Welcome to solverfy.
Here we're looking at a cart moving down an incline of 20 degrees, and it is attached to a spring on the back end via 3 pulleys. So how we are going to be working with this system is through use of conservation of energy. There will be 3 forms of energy that we will need to consider at our initial point and our final point. And I show the 3 forms. There's kinetic energy, which is going to be 0 up at the top of the drop, so to speak. There's gravitational potential energy that depends on the y-coordinate, which is equal to basically mg d sine of theta with a negative sign. So I'm going to choose my reference point at the top of the incline. And sorry, that's not equal to y, that is equal to u grav. So just a note that my reference point is not the top of the incline, but at top of drop at d equals to 0, with the understanding that the cart is moving down the incline. So the gravitational potential energy will be decreasing, turning more negative. And then finally, the spring potential energy. As the cart moves down the incline, the spring will stretch from its initial value. Let me write that down. S is going to be equal to 3 times d plus the initial stretch. And why it's 3 is because the rope that attaches to the cart is stretched over a pulley 3 times. So there are 3 lengths of that rope that go through a pulley, and that is going to triple the length of the spring that gets stretched as the cart moves down the incline. Okay, so the first case that we're going to look at is how much velocity does the cart acquire when d equals 10 centimeters. We'll put that into meters. And so we want to write down a balance equation. And so we have initial kinetic energy is 0, and initial gravitational potential energy, because of my reference point, is 0. And then we have 1/2 K, which is 300 newtons per meter, times the initial stretch in meters squared. And all that has to equal, on the other side, the balance, 1/2 60 V final squared for the final kinetic energy, minus 60 times g times d sine of 20 degrees for the potential energy, which is dropping, and plus 1/2 K times 3D plus the 25 millimeters squared. Turn that into meters. So I'll put one intermediate step, but basically what we have on the left-hand side is 9. Whoops, let me use a different color. 9.375 times 10 to the minus 2 equals 30 VF squared minus 20.11 plus 15.84. And without further ado, I'll just include the final answer. After some algebra and taking a square root, we wind up with a velocity of a reasonable value in meters per second, 0.381. So let's take a look at a second case. Let's find out how far the cart slides down the incline when its final velocity equals 0. So it's starting up the top with 0 velocity, but we'll continue down the incline until the spring develops enough backwards force to hold the cart temporarily in place. So the right-hand side, we're going to say, is not going to change any. So we still have that initial spring stretch energy. Finally, though, we have 0 kinetic energy. And we now have an unknown distance down the incline that goes into our gravitational potential. And let me go ahead and multiply out the m times the g times the sine of 20 degrees. Would be 201.11 d. And then let's see if we've got plus 1/2 times k. So that would be 300 times SI, which is the 0.025 plus 3d squared. Okay, now let me simplify all this down into a quadratic equation. So this will turn out to give us a quadratic equation in D. And as we'll see, the quadratic equation is not too hard to solve. What we wind up with is, after some algebra, I'll write the intermediate step is minus 178.60 plus 1350 d squared. And that can be factored out into a simple binomial. Thankfully, we do not need the nasty looking quadratic equation to work with this. Okay, so that can be factored into two factors, both of which must equal 0. So one of the solutions is d equals 0, and that is the solution for the top of the drop. So that does make some sense. And then the second solution is 178.6 divided by 1350 in meters, and that is equal to 0.132 meters. So it will continue to fall for a little bit beyond the 10 centimeters before it stops and bounces back up to the up the incline.